Kia ora team, Mr. Dharma here. I just wanted to go over the Trigonometry Trevor's Tractor practice assessment. But before you have a watch of my video, please try do this yourself and see how you get on. Okay? So let's read. Trevor has a tractor with a diameter of 1.6. Trevor's neighbour, Farmer Fred, also has a tractor with a back wheel radius of 0.8. This is key. One's got a diameter, one's got a radius. But if you look at it, they're actually the same, because the diameter is twice as big as the radius. That's something we might need to know. One morning, Fred and Trevor are parked outside Trevor's barn before heading out to plough the fields. Trevor notices that there is a mark on both tractors' rear tyres. The mark happens to be at the lowest point of Trevor's wheel. So the lowest point of Trevor's wheel before he drives off. The mark is at the axle height above the ground of Fred's wheel and is positioned so that it moves down as he drives off. So I kind of want to picture that. So if I were to draw a wheel, if we call this Trevor's wheel, the mark is here. Whereas Fred's wheel, the mark is, well, if we follow the way he's going, the mark is here. Because when he moves forward, this mark will move down. Okay? It's at the axle height, and the axle's in the middle, but is ready to move down as he drives off. Does that kind of make sense, the difference between Trevor's position and Fred's position? Fred's is here, ready to move down, and Trevor's is already at the bottom. Okay, so let's see what we need to do. Find models that represent the height of the mark on the back tyre for both Fred and Trevor's in terms of the distance travelled. Then there's some problems to solve. Let's look at this then. So if this starts here, as it goes around, let's talk about Trevor. So I'm gonna actually do this in red. So Trevor starts at the bottom, and then as it moves around, gets to the middle, then gets to the top, then gets to the middle, then gets to the bottom. So if I would draw that, this is what Trevor's model will look like. And of course it carries through and repeats. Okay, but that's a rough estimate for me. Okay, and let's have a look at what Fred's looks like. Well, Fred's very similar to Trevor's. Sorry, let me try that again. And Fred's starts in the middle, but goes down to the bottom, and then goes back up, then to the top, then back down. So that looks more like that kind of shape. And these are the key points for Fred. And these are the key points for Trevor. Okay, so these are the two graphs that we've got. Okay, now let's figure out what the max and the min are. Well, let's look at the maximum. The highest it can go is off the ground, which is 1.6 meters. And the lowest, obviously, is on the ground of 0 meters. And Fred's, the radius is 0.8, so the highest it can go is 1.6, and the lowest is 0. Okay, so can we find out what A and D are? Of course you can. So for Trevor, A is the amplitude, which is the max minus the min divided by 2, which is 0.8, and D is the max plus the min divided by 2, which is also 0.8. Okay? And B, well, what is the period? How long or how far are we traveling? Let's quickly have a look. For the one wheel to rotate, what's the distance the wheel is moving? This is not a time question, this is a distance. So what is the distance travelled if this spins one revolution? Well, the distance travelled is that circumference, right? So the distance is 2 pi times the radius, which is 0.8. Okay, so that is actually 1.6 times pi. Okay, so that's the distance, and that is also the period. So 2 pi on 1.6 pi, because this is t. Okay, and then what's c? Well, c is the shift. And depending on if you do a sine model or a cosine model, this will change. But for the sine model, you'll use this point. For a cosine model, you use this point. So let's do both of them. For a sine model, if this is 1.6 pi, then this is 0.8 pi, and then this must be 0.4 pi, and this is 1.2 pi. And I'm just doing this by halving, right? Half of this and half of this again. Or if I do the same thing for Fred, it's the same thing, right? It's the same amount of distance, the circumference, which is pi times the diameter, which is pi times 1.6. This is 0.8 pi, if this is a sine model. And once again, if we're doing a cosine model, we need this point, which is 1.2 pi. And once again, this is 0.4 pi. And so I've used pi in all my answers, okay? I don't need the horrible decimal form. So if you guys are going to do a sine model, I'd use 0.4 for Trevor. If you're doing a cosine model, you're going to use 0.8 pi. Okay? This is Trevor's. Okay? And let's check that soon. Okay, let me just write this. Sine, and this is cosine. Right? And then let's do Fred's. Fred's is going to be A is the same because it's the same height. D is the same. The period is 2 pi on 1.6. So that's the frequency. The period is the same also. It's the same distance travelled. This time, C is slightly different. If it's a sine model, you use 0.8 because that's the start of the sine curve. Or if it's a cosine, you'd use 1.2 pi. Okay, remember this is sine, and this is cosine. Okay, so once you've got that, we can form models, right? What I'm going to do is I'm going to type this into Desmos and see what we get. So I'm going to move on to Desmos, and you tell me if this makes sense. Right, here we go. So on Desmos, I'm going to use this information for distance. This is Trevor's distance. I'll do it in X, that's okay. Trevor's, this is going to be 0.8, because that was A. Sine, I'm going to use the sine model. 2 pi on 1.6 pi, right? You can simplify that as you would. The pi's would cancel, and you could You can change it, but I'm going to just leave it as is for now. You can deal with the ins and outs of that. Right? And then it would be x minus 0.4 pi. Okay? Plus, what was d? D was also 0.8. Okay, let's just move this along and see if that makes sense. And we'll just change the settings, and we'll make the x will go from, once again, let's go from 0 to, say, 10. Let's go y will go from negative 0.2 to maybe 2, so we can just see that model. Right? We'll go from about negative 1 to about 11. Okay, that's really good to just have more than what you want on the graph. Okay, so this is the model, and let's see, it starts at the bottom, goes back to the top, goes to the bottom, goes to the top. Fantastic. And let's see if we can do Fred's model as well. So Fred, also the same x, so same amplitude, sine 2 pi on 1.6 pi. We will simplify this soon, but I just want to do a rough guess. Okay, 0.8 pi plus 0.8. Okay, and let's just see that that makes sense as well. I'm going to just move this along a bit so I can see the whole graph. So, do we start in the middle? Yep. Do we go down? Then do we go up and then come back to the middle? Yes, we do. So these are my two graphs, and so my models work. Okay? Now, that is kind of useful for us. So if you do decide to simplify, you can make it look prettier. The pi's will cancel. The pi will cancel. And this is the same as 20 on 16. Sorry, that looks horrifying. And 20 over 16 is the same. If you divide both by 4, it's 5 over 4. And the same thing here is 5 over 4. Okay? So there are my graphs. It looks a lot cleaner this way. Okay, so 5 over 4, once again, you can rewrite as 1.25 if you so want. Right? But I'm going to leave that to your discretion, however you want to run with that. Okay, 5 over 4 is 1.25. It might be a lot prettier to run with. So maybe I will do that. 1.25. 1.25 for those of us really keen on the decimals today. Okay? Okay. Now, notice that these are both sine models. I'm going to now do these as cosine models just to check that they work. Right? And so I'm going to go t, and this time we're going to have cosine. Just going to show you that it works. Is going to be and 0.8 cosine, and on my document I had the first one was this 1.125 is still going to be there, and then it's x minus 0.8 pi plus 0.8. And notice this covers that red line, meaning the model is correct. And then if I do the f for the cosine as well, 0.8 cosine 1.25 x minus 1.2 pi, close brackets, plus 0.8. Hey, this purple covers the blue. Right, so we know the models are working. And in fact, what I might just do is I might just type it like this so you know what I've used. Right? That's just me labeling what kind of model I'm using. That one's the sine model, so T for Trevor and F for Fred. Okay? So if you use the sine models, those are the two equations you'd use. If you use the cosine models, these are the two equations you'd use. Alright, so now let's see what the next part of the question is asking us to do. Right? So we're going back to the question. What do we have? We've modelled them. I'm happy with those two models. Find the distances when the mark on Trevor's tyre is above 1 metre. Find the distances when the mark on Trevor's tyre is 1 metre above the ground in the first 10 metres that he travels. Okay, so let's do this pictorially first. So let's go back to Desmos. So we're just looking at Trevor, and I'm going to get rid of all of this. I'm going to just use this. And what I want to know is, in the first 10 metres, so I've got 0 to 10 along this axis. In the first 10 metres, and so I might just label it distance travelled, distance in metres, and then height of the mark in metres also, right? Because that's kind of key for us, right? This is probably one of the first few times we've done a distance versus distance graph, but it should work done the same. So in this, when is it above 1? And you can intuitively see it's this hump and this hump. So let's just plot that though. Let's go y equals 1, okay? Because you can actually click these solutions. So you can go, it's going to be between this and this, and it's going to be between this and this. So, but we should be able to solve that, right? Because reading off a graph isn't trigonometry. So let's get these ranges. So it should be from here to here and from here to here. We know the answers, let's work them out. Okay? So we're going to do that on Desmos, on our whiteboard. So how do we do that? So first off, let's take Trevor's equation. Trevor's equation was 0.8 sine or cosine. For this one, I'm going to use sine. Brackets 1.25 x minus 0.4 pi plus 0.8, and we want to see when is this equal to 1, right? So first off, we subtract 0.8 from both sides. We get 0.2. Then divide both sides by 0.8. So 0.2 divided by 0.8 is 0.25. You can check it if you want. Sorry guys, something's weird with my mouse today. So, now to solve this general solution, we could solve it just normally, but you know, we should get a general solution. But you go sine inverse of this side equals 1.25 x minus 0.4 pi. Okay, and then sine inverse of this side will be really important to us, and this will be our alpha, and this will be our theta. Right? I've done it backwards to how I normally do it, but only because I had the equation on this side. So really quickly, so what is sine inverse of this? So you type in what is arcsine of 0.25, or what is sine inverse of 0.25, and the answer is 0.25 to 724 dp. Okay? Okay, and this side is going to be the same, right? This side doesn't change, right? But now I can write the general solution. I'm going to just put this over the side for the general solution. It's going to be 1.25 x minus 0.4 pi equals it's going to equal n pi plus -1 to the n of 0.2527. And now I have to solve for x. So I divide by 1.25 and I go through the processes. And solving this general solution should give me the answer I want.